MooseKV is a cloud-native key-value storage system consisting of a standalone LSM tree storage service, an API server, and a web UI. All these system components are encapsulated into Docker images and thus require no effort to deploy on different machines. It helps developers to easily install and verify the effectiveness of the flexible LSM tree structure for their own applications and workloads. This is the web UI of MooseKV. Developers can specify their working conditions by editing the parameters that are presented here. In this demonstration, we use the block page size of 4096 byte to set the tuning environment. For the dataset information, we set the total number of entries to 22 million and key value size to 1 kilobyte. Moreover, the size of the write buffer and the bits per key for the Bloom filter are specified as 2 megabytes and 5 respectively. To meet the requirement of some practical applications, users are allowed to designate the size of the last level, thus directly editing the LSM tree structure. Here we assign 0 entries to the last level, which means MooseKV can freely assign any number of entities for optimizing the structure. In the storage layer, MooseKV incorporates Moose to configure its LSM tree. Moose is demonstrated to be able to deliver satisfactory overall performance for its flexible structure and extensive design space. After left-clicking the Compute button, MooseKV will automatically calculate the desirable structures and present through the web UI. For a clearer exhibition, the structure of the derived LSM tree and associated parameters, including capability and number of runs, are visualized on the screen. The blocks represent sorted runs in each level that are differentiated with color. Here, please note that the number of runs at each level of the LSM tree significantly influences the trade-off among the efficiency of different operations, including update, point lookup, and range lookup. To facilitate a wider range of applications, MooseKV introduces a parameter k to adjust it and visualize its influence with a Pareto curve. This Pareto curve indicates that one operation, such as update, could not be further optimized without affecting the others like point lookup and range lookup. Users could tune the number of runs according to their own applications by directly moving the slider of k on the web UI. As is shown on the screen, an enlarged k value leads to an increase in the number of runs, thus being beneficial for update-intensive applications such as log collection and social network services. When a certain structure is selected, users could start to create a Moose instance by left-clicking the Start Server button. This prompts the creation of a new pod within the Kubernetes API server, followed by an asynchronous instantiating of LSM tree based on the determined parameters. At current, an LSM tree instance can be accessed as a storage engine via RESTful APIs and HTTP protocol. Here we run a workload of operations with 1 million operations consisting of a balanced number of updates, point lookups, and range lookups. To assist users in evaluating the system performance, MooseKV incorporates diverse figures and tables in the monitoring interface. They can be conveniently visualized by clicking on the Monitor button on the top of the web UI. When running an LSM tree storage engine, MooseKV automatically gathers various statistics and metrics concerning system status periodically, and updates the associated counterparts in real time. Here we can check. The latency of update, point lookup, and range lookup operations is recorded in a line graph and updated over time. The latency indicates the average time used by each operation, which is the most explicit and important metric for system performance evaluation. Additionally, MooseKV breaks down the entire workload into different operation categories to collect their operation number and the associated ratios, as is exhibited in the pie graph. To monitor the behavior of compaction, an impactful factor in the overall performance, MooseKV introduces a bar graph to display the associated statistics across the entire working process. Additionally, the table presents many other important information such as the flush bytes, key number, and Bloom filter FPR. With this profiling, users are able to identify the demerits of the current system and figure out how to optimize it through a careful analysis. This brings us to the end of this demonstration. Please feel free to contact us if there is any question. Thanks for your watching.